Hi, good afternoon. So today we're talking about acids and bases and titrations. Here's a nice image of indicator phenolphthalein turning pink when it becomes basic. You can see that, and this would be maybe a sodium hydroxide and the burette and hydrochloric acid in the Erlenmeyer. We'll talk about that more later. But so an acid is something that when added to water, it increases the concentration of hydrogen ions. So that would be something like hydrochloric acid. You can see here HCl breaks apart into H plus and Cl minus, while a base is something that will increase the hydroxide ion in solution. That's the Arrhenius definition. So something like sodium hydroxide dissociates to form sodium and hydroxide. And then binary acids are molecular compounds. They're made up of two atoms and dissociate in water to form the proton and the counter ion, the chloride ion in this case. So hydrochloric acid is what's considered a strong acid. You can see in this cartoon picture that all the ions are broken apart separately. The H plus and then the chloride minus. Well, a weak acid, some of the ions are still staying together as a reactant. So HCl breaks up 100% into H plus Cl minus, while hydrofluoric acid has an equilibrium of H plus and the conjugate base, the fluoride ion. So the fluoride ion would actually react with the water or interact with the water and form some of the original acid if you were just to put something like sodium fluoride in the water. So that becomes more important when we talk about weak acids and weak bases later. But to start off, here's a list of strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. The binary acids, HI, HCl, HBr, you say hydro in front, and that tells you it's a binary acid. Well, something like chloric acid, that tells you it's the oxy ion. So ClO3 minus the chlorate becomes chloric acid. 8 becomes ic. And if it's an ite ion, it becomes an OUS acid. So just some nomenclature there. If it's not a strong acid, then it's a weak acid. And here's some examples. I mentioned hydrofluoric acid earlier. And then here's the associated Ka values with that. The Ka value is the equilibrium constant expression value. So if we have something like hydrofluoric acid, it breaks apart into the hydronium ion or proton and the fluoride anion. And these would be aqueous. And so the products over the reactants will equal the equilibrium expression constant. So it's a ratio of these values. So if it's got some back reaction, then there's a value associated with this. So for hydrofluoric acid, it's 6.8 times 10 to the minus 4. So it's telling you there's some of the reactant involved with that. Well, something like these guys, they go 100% to the products, so there's no Ka associated with that. It would be infinite Ka if you were going to calculate that, because the denominator would be 0 technically. So when you have the strong base, that dissociates into sodium and hydroxide ion, or here's some other example of it. But when you have a strong base and a strong acid, then what happens is you get a neutralization reaction. So they're both equally contributing the proton, it's HBr, or the hydroxide. So the hydroxide and the proton, hydronium, end up forming the water together. So it neutralizes it, and leaving behind the cation and anion associated with the base and the acid, and those sodium and bromide in this case would be the salt. This is essentially one of the double displacement type reactions, because the sodium changes place with the proton. So you get sodium bromide and HOH, which is water. So if you think about it as a double displacement reaction, that's shown here. But it's a special case of a double displacement reaction, which is a neutralization reaction. So that's what happens here, is a neutralization. And here's another example: hydrochloric acid and potassium hydroxide forming potassium chloride and water. So a titration is a way to measure the concentration of these reactants. So if you have an unknown concentration of your acid or base, and you put an indicator like phenolphthalein, this is a molecule that is showing color at pH 8.3 to 10, and we're colorless at 0 to 8. So you can see here, it's colorless, and versus this is a fuchsia color, which I showed in the beginning of our presentation here. You can see that pretty nice pink color there. And in fact, at low pH, it sometimes forms an orange red. And if you go above pH 10, it goes back to colorless. And it has to do with the conjugated pi bonds and how it protonates and deprotonates. But you can see here, the indicator would change around here, and that's when we have our dramatic pH shift. So we approximate the endpoint of the titration to the equivalence point of this curve, where we have equal base, and acid. Equal moles. So here's a way to solve these problems. Step one, determine the moles of the base or the acid. And then use the stoichiometry of the equation to figure out the amount of moles that you would need of your unknown. And then finally, you can calculate the molarity of the final solution if you know the final volume. So here's an example of a simple problem at an equivalence point. So sodium hydroxide with hydrochloric acid. So the first thing you kind of want to do is write the formula out. NaOH plus HCl form NaCl plus HOH or H2O. And that allows us to think about what we have in our solution. So this says we have 42 milliliters of 0.1 molar sodium hydroxide. So our volume, and I'm going to convert this to liters, 0.042 liters sodium hydroxide, and our molarity is 0.150 moles per liter. And remember, molarity equals moles per liter. So if you multiply both sides times liters, liter times molarity will give you moles, or volume times molarity. So we have our volume here. We multiply the molarity, and then we'll get our moles. So 0.042 liters times 0.150 molarity gives us the moles, 0.0063 moles. And then the hydrochloric acid, we're told we have 0.050 liters of HCl. So what's the molarity of the acid solution? Well, we know the moles of the base here, and at the equivalence point, the moles of the base should equal the moles of the acid, because we'd have it neutral at that point. So when the moles of the base and the moles of the acid are equal to each other, we have our equivalence point here. So that's when you'll see the color change. So the molarity of the acid equals the moles of the base, actually, because the moles of the base equals the moles of the acid in this case. So moles base to moles of acid. You can see it's a 1-to-1 ratio here. So 0.0063 moles acid divided by the volume of the acid, 0.050 liters. So we get 0.126 molarity. So that's a standard kind of equivalence point titration problem. Maybe you had those in general chemistry before. And again, you can see here's the base. We know the amount of base added because we look at the volume change, how much volume changes when it changes color. And then we know the concentration of the base because we created that solution. And then we know the volume of the acid because we dispensed that into our Erlenmeyer down here. So to find the molarity of the acid, we just take the moles of the base, and it's 1-to-1. So we know the identity of the acid, and then we're able to determine the moles of the base, which in turn is the moles of the acid, because it's 1-to-1. And then take that value and divide it, and we get our molarity. Now, another type of problem that we have is the titration problem at non-equivalence values. So we'll start with a strong acid and strong base for this video, and then in the next video, I'll go over a weak base or weak acid with a strong base acid. It's kind of combination. So what we have here, consider the titration of 100 milliliters of a 0.1 molar or mole per liter solution of sodium hydroxide. And it's with hydrobromic acid. So recall hydrobromic acid is one of our strong acids. You can see here, hydrobromic acid. So we have a strong base, strong acid type problem. So let's write out our equation. Sodium hydroxide plus hydrobromic acid make a double displacement reaction to form the sodium goes with the bromide, and the proton goes with the water, OH, to form water. So HOH plus NaBr. These are all aqueous, HOH, and water is actually going to be a liquid. So the molarity, they gave us that value. Sodium hydroxide, 0.100. And the volume, I'm going to convert this to liters. So you move that over 3 units over 100 milliliters. Milliliters to liters. The one with the metric prefix, 10 to the minus 3, we get 0.100 liters. This is moles per liter. So when you take the product of these two, the liters cancel out, and we get moles. So the moles of sodium hydroxide is 0.01. So how much HBr do we have? Well, we know it's 1 molar solution. I'm going to write that moles per liter. And when we start off, we have 0 volume added of HBr. So 0. So that means we have 0 moles of HBr. So that means we have all strong acid. So it's simply NaOH dissociating 100% because it's strong into sodium cation plus hydronium anion. So you have 0.1 moles of sodium hydroxide from our calculation here, forming 0.1 moles of the sodium ion and 0.1 moles of the hydroxide ion. So what's the pH? Well, the pH is the negative log of the H. Negative log of the hydronium ion. So this is the hydroxide. So we don't know the hydronium, but we know the hydroxide. So if we find the POH, negative log of 0.100, then we can find the POH, and then from that we can find the pH. So the negative log of 0.1 is 1. So our POH equals 1. So our pH equals 14 minus 1, which is 13. Where did I get that? Well, pH plus POH equals 14, right? So minus POH to both sides, minus POH. So 14 minus 1 equals 13. So our initial pH of the sodium hydroxide solution before we add any HBr is 13. So now let's think about the next step. We've now added, we're going to add 1 milliliter. So we have sodium hydroxide plus hydrobromic acid. And we know the molarity again is 0.100. The volume is 0.100. So our moles of sodium hydroxide, when you do the multiplication of those two, you get 0.0100 moles. The HBr, we know our volume's 1 milliliter. So that's 0.001 liters. 0.001 liter. And our concentration at HBr is 1 molar. So molarity times volume equals moles. So 1 moles per liter times 0.001 liters equals 0.001 moles. So let's write that down here, 0.001 moles. So you can see there's more NaOH than HBr. So what happens is all the HBr is going to be converted into product. So NaOH plus HBr forms water and salt NaBr. So we start off with 0.010, and we're going to react that with 0.001 HBr. So our change, subtract that out, 0.001. Zero, zero, one. So all the HBr is going to be consumed. It's going to turn into our product, which is water and salt. So which means that when we've established our equilibrium for our products, it's 0.01 minus 0.001. So we have 0.009 moles of sodium hydroxide. And then no more acid. And then these guys, they're spectator ions. So that's the moles of our sodium hydroxide. So we know sodium hydroxide dissociates to form the sodium and the hydroxide ion. So if we have 0.009 sodium hydroxide, we have 0.009 moles of hydroxide ion. Now, negative log of our hydroxide ion concentration gives us the POH. So if we take the negative log of our molarity of OH, we can find our POH. Be careful, this is the moles. So what's our total volume? Well, we started with 0.1 liters of sodium hydroxide and 0.001 liters of HBr. So our total volume is 0.100. Sorry, 0.101 liters. So 0.09 divided by 0.101. So 0.009 divided by 0.101. We get the negative log of 0.8089. So the negative log of that is 1.05. So that's our pH. So our pH is equal to that. So I hope that helps you figure out how to determine the pH at different additions of the acid. Oh, that's the POH, right? Because that's the hydroxide concentration. So recall 14 minus 1.05 is 12.95. So that's actually our pH there. So because pH plus POH equals 14. So you got to take that POH and find the pH. So it's really important to understand that before you have equal mole amounts, that the pH is dependent on excess sodium hydroxide concentration. So that's kind of what's going to happen here until we get to equal mole amount. So we could figure out that volume of equal mole amount. So 0.100 liters times 0.100 moles per liter equals 0.01 moles of sodium hydroxide. So what volume are we going to need of this to have equal mole amount of HBr? So 1.00 moles per liter of HBr we want to know the volume of that to get 0.01 moles. So if we divide our molarity, moles per liter, then the moles cancel out and the liters comes to the top. And we know it's 0.01 liters or 10 milliliters of HBr at equivalence point. So that's right here, 10. So all these volumes, 5, 9, 9.9, that's before the equivalence point. So something to think about with this problem. So that's confusing. Let's look at this a little bit closer again. So we have sodium hydroxide plus hydrobromic acid forming water and salt, our sodium bromide salt. Normality of the sodium hydroxide 0.1. Our volume is 0.1 liters. So if we multiply those, we get our moles. Sodium hydroxide. So now let's look at, say, 5 milliliters or 0.05, 0.005 liters of HBr, 1 molar. Take the product of those, liters cancels, and we'll get 0.005 moles HBr. So 0.005 is less than 0.01 moles. So we have excess sodium hydroxide in this case again. Our total volume is equal to 0.1 plus 0.005. So 0.1005. 0.105 liters, or 105 milliliters, if you think about it like that. So we now know if we take the difference, so this sodium hydroxide is in excess, we add it to the HBr. So the HBr is all going to get converted into product, leaving behind 0.05 moles of sodium hydroxide, because sodium hydroxide minus the hydrobromic acid 0.01 minus 0.005, and you get 0.005 of sodium hydroxide left. So that breaks apart into the sodium and the hydroxide. You know, it's 100% dissociation, so there's no back reaction. It's a strong base, so it's 0.005 OH minus. So let's find the pH of that. Negative log of the molarity of OH minus is POH. So 0.005 moles sodium hydroxide over our total volume, 0.105 gives us the molarity of our POH, of our OH minus, sorry, it's not POH, we didn't take the negative log yet, 0.0476. So take the negative log of 0.0476, and we get 1 POH equals 1.322. 14 minus 1.322 is the pH, which equals 12.68. So that's our final answer for this part. So you could go through and do the same calculation for 9 and 9.9. You'll find there's excess sodium hydroxide, and you'll get values approaching that 7 or the equivalence point. Let's jump ahead to do the equivalence point now. So 10, that's when we have equal amounts. So we know 9 and 9.9, it's excess sodium hydroxide. So you'll go through the exact same calculation we just did. NaOH plus HCl goes to NaCl plus HOH. Oh, it's HBr. So used to doing hydrochloric acid. So we have 0.1 volume, molarity 0.1, so moles 0.01. And now HBr is 1 mole per liter and 10 milliliters, or 0.01 liters. So that product of this becomes 0.01 liters of HBr. So you can see these are equal to each other. So there's no excess sodium hydroxide and no excess HBr. So it's all products. So it's 0.01 moles of NABr and 0.01 moles of HOH. They're consumed 1 to 1. So the pH is dependent on our HOH. Which from dissociating that, we know it goes from H plus OH minus, that equals 1 times 10 to the minus 14 for our KW. So we have equal amount of H plus and OH minus. So each of these values is 1 times 10 to the minus 7. Remember, KW equals product over reactant, and water is a liquid in this case, so we leave it off of our equilibrium expression. So 1 times 10 to the minus 14 equals H plus and OH minus. So these are equal amounts of each other. So 1 times 10 to the minus 14 equals x squared. So you take the square root of that, and you get 1 times 10 to the minus 7. So the negative log of 1 times 10 to the minus 7 is 7. That's what our pH is. Our pOH also equals 7, but that doesn't matter because 14 minus 7 is 7. So it all comes out the same, neutral. So I hope that makes sense. Let me know if you have questions about that. And then finally, let's look at after we do this guy here. So after the equivalence point, NaOH plus HBr, hydrobromic acid, form water, HOH, and sodium bromide. So we have, again, same thing, 0.100 moles per liter, 0.1 liters. That gives us 0.01 moles of NaOH, sodium hydroxide. HBr, let's look at, let's go to the 12 milliliters. So that's 0.012 liters. And we have 1.00 moles per liter. So you take the product of those, you're going to get 0.012 moles of HBr. So molarity times volume equals moles. That's what I did here. Multiply these. So the liters will cancel out. So now you see there's extra HBr. If you subtract 0.01 minus 0.012, you get negative 0.002. So you can't have negative moles of hydroxide. So what's happening is there's excess HBr. So all the 0.1 moles of HBr is reacting, and then we have really what's happening, subtract out the base moles, leaving us 0.002 moles of HBr. Now we have a strong base, strong acid instead of a strong base. So that's H plus Br minus. So it's 0.02 moles HBr is 0.02 moles of H plus and 0.02 moles of Br minus. And then negative log of H plus, the concentration of that is pH. So we have to find the concentration. So we know this is the moles. Concentration is moles per liter. So 0.002 moles for what's our volume? 12 milliliters plus 100 milliliters equals 112 milliliters, which is 0.112. 0.112. So 0.002 divided by 0.112 is equal to 0.0178. 0.0178. Sorry, I ran out of room. And so let's find the pH. Negative log of 0.0178 is 1.75. So that's our final pH. So that's the end of this problem. I skipped doing 10.1, but you could do that too. It'll be between 1.75 and 7. So I hope that's helpful. If you want me to continue to do some of those other calculations, let me know. The next video we'll do weak base, weak acid, or hopefully that prepares you for that.